Okay, magnetic field and infinite line current. So we have an infinite line here, and we got a current I. And we want to find the magnetic field at some distance A. Okay? So what we have to do is we have to think in terms of a typical delta R, or delta L. So here's a delta L. Now, over here, it didn't matter where delta L was on the circumference. You got the same magnitude of the field and the same direction of the field contribution for that delta L, right? But here, it matters. The further you are, because not every point on the line is clearly at the same distance from this point, right? So the further you are, the less field you're going to get for two reasons. Number one, the R squared is greater. And number two, the cross product.
Did you ever get my grade?
Well, the cross product depends on the sine of this angle, right? Sine of the angle between, well, the sine of the angle between delta L and the R vector. So here's your R vector, and you got this angle theta here. So the further this point is from the point directly across from the point at which we're calculating the field, the smaller the sine of the angle is, as well as the greater the distance, right? So what this means is the contributions, when you get, maybe this far away, maybe 3 or 4 times further from the point than the point is from the line, the R squared and the sine of theta become so small that the rest of the integral doesn't make a big difference. You probably have at least 90% of your integral, and you can work that out. You probably have at least 90% of your integral from, let's say, 4 times the, just between 4 times A on this side and 4 times A on this side of this point. Okay? Now I'm just doing that intuitively. But at 4 times the distance, you got 1/4 squared, 1/16 field already, and the sine of that angle is like 1/4. Okay, so you got 1/64 of the contribution from this a segment here than you do from a segment here, and it keeps dropping off rapidly. Okay, so you can work that out. I don't know exactly at what distance we can really say you've already got 90% of your field, but the application of this is that if you have a long wire, how long is long enough to make it infinite? Well, as long as this is a lot closer, as long as your point is a lot closer to the wire than it is to the ends of the wire, it's pretty much going to act as an infinite wire. Okay? So in this close neighborhood of a wire, as long as the wire's got some length, this is what you've got. In particular, if you got a loop close to the loop, our result here, the closer you get to the loop, the better this result is going to apply as opposed to the result for the field at the center. And that's interesting to work out. Now, we're not going to work it out because we don't have time. I think we've got what? Oh, geez, let's see. So we got 52 minutes of this class left. So we better hurry up. Okay, now, here's what we've got. Okay? So, we're going to impose a coordinate system here. We're going to say that this is the x-axis, and x equals 0 at this point. So what do you think we're going to need in order to set up or to calculate the delta B from this segment? What don't we have that we're going to need? Starts with S. We need a sample point in this increment. Okay? Okay, so if we've got that sample point now, work it out.
Where is the sample?
I mean, just, it's somewhere in here.
All right.
We don't care. We're gonna let delta L approach 0, so it's gonna really get confined, right? Okay? So, what's the delta B corresponding to this increment? And then, what integral do you get, and evaluate it.